So I take 2 hours. I think I'll ask them if they want a break or they don't want a break. Okay, so today I'll start from I'll take 2 hours. So do you people want a break in between? Do you need a break in between the class? I mean, around 12:15 or 12:20, like that? Can you hear me?
Yes, ma'am.
You can hear me. Okay, so do you need a break? Because I'm planning to take up to 1:30. So do you need a break in between for 5-10 minutes?
Yes, ma'am, it will be good.
Okay, so what I'll do is now it's around, okay, so according to this watch, it's around 11:22. So maybe around 12:25, 12:20 like that, we'll take a break for 5 minutes and then I'll start again at 12:30. Is that fine? Okay.
Yes.
So let's continue again. Let me continue with where I left off yesterday. Something isotropic. If I rotate the coordinate axis, then the components must remain the same. And I've already given you examples of those. So one is delta ij. This is a second rank tensor, which we saw is also a symmetric tensor. The other is the totally antisymmetric third rank tensor, the Levi-Civita tensor, epsilon ijk. Then I also told you that if you want a vector which is isotropic, then the only vector which is isotropic is the trivial one, which is a zero vector. Now, the most general, if you want, so these are at least examples of two isotropic tensors. Now, I can ask the question that what is the most general second rank isotropic second rank tensor? So, if it is a second rank tensor, then you know that it must be having two indices or two subscripts. So, most generally, at least I can say it should be Tij. And when I say it's isotropic, what it means is that these components must be the same. So, but whatever basis I go from, say I start from some basis P and then I go to some other basis P prime, and whatever be the rotation, this condition must be satisfied for all ij's. Or in other words, all the 9 elements must satisfy this for any arbitrary rotation transformation. So demanding this, because we know what is the left hand side. Left hand side tells me that this is equal to Rik, Rjl, Tk. And this should be equal to left and right hand side. It should be equal to Tij. Okay, so this particular condition now that Rik, Rjl, Tkl equal to Tij, or actually it's a set of 9 conditions, and that must be true for any arbitrary rotation matrices. And again, as I said, let's restrict for the time being to determinant R equal to +1 rotation matrices. That itself will impose constraints on what possible values this Tij can have, and what one can show is, so what you can do is, the way to prove this is the following: take this and take, say for example, T11 here. So I need T prime 11 should be equal to T11, or in other words, that will tell me T1k, T1l, Tkl should be equal to this. Okay, so suppose, I just illustrate how one can do. Let I equal to 1, j equal to 1. Then what this implies is that R1k, R1l, Tkl must be equal to T1. Okay. Then what you do is choose some particular Rs, and try to see what conditions you will get. Because you see here I'm summing about all k's and all n's. So in this, all the elements, all the 9 elements will get mixed up or will come into play. So it will give you some conditions on what relations between these elements of Tkl and T11. Okay, and take some specific R. For example, you can I can tell you, you can take take rotation by pi by 2 about the z axis, for example. So once you take a specific rotation matrix, you know the elements of R's, use that, and then get some relations between these, and that will impose some constraints. And from that, okay, I will now tell you the answer. One can show that the most general second rank tensor, by doing this, you can show that it can be only this, where lambda is a scale. So essentially, it's by solving this, one can show this, okay? One can show this, okay? So most general isotropic tensor of rank 2. So at least for rank 2, what we find is that we don't get a trivial answer, because for rank 1 we got simply a trivial answer, that is a zero vector. Here I do get a non-trivial answer, but it is simply some scalar times or delta h. Similarly for rank 3, and you do the same thing for rank 3. So now you will get T prime ijk should be equal to T ijk. I should get some 27 relations, and again use these transformation properties to get the constraints. And again, what you can show is that for rank 3, I should get the most general one is simply of this one. Again, lambda is a scale. So for rank 2 and rank 3 isotropic tensors, the most general ones are simply your delta ij and epsilon ijk multiplied by some scale. Now I can ask, what about a rank 4 tensor? What will be the most general rank 4 tensor? At least can we write down an isotropic rank 4 tensor? At least one example can be write down. Given that you know this, that the second rank tensor is, say, isotropic tensor is delta ij and third rank is this, can you write down at least one isotropic fourth rank tensor? And using whatever we have learned earlier. Can you, okay, let me give you a hint. Construct them from what you know already. You know second rank tensor which is isotropic, you know third rank tensor which is isotropic. From that, can you construct a fourth rank tensor? Nobody is able to attempt it. Okay, let me ask you this. Suppose I consider this object, delta ij, delta kl. Okay, and let me call this as aij, kl equal to this. What will this object transform like?
Tensor rank 4.
It's a tensor of rank 4 because we have just combined two tensors of rank 2. Okay, now is this an isotropic tensor? What will be the values of, okay, how many components or how many elements will this A have?
3.
Huh? Just 3. It's a fourth rank tensor. So in fourth rank tensor, we have how many components in all?
And 3 to the power 4.
3 to the power of 4. So it has 3 to the power of 4 components, which is equal to 81 components. Right? Okay. Now can you tell me what will be the values of these components, 81 components? At least some of them you can tell. I have given like this, and if I define it like this, what will be the values of this? Suppose I have A1 to KL. Can you tell me what answer should be?
0.
Should be 0, obviously. Because by definition, the right hand side is going to be 0 unless I equal to G. So already you can see that if I is not equal to j or k not equal to L, then this is going to become identically equal to 0. So you know, like, so I can simply write that aij k equal to 0 if I not equal to 0, oh sorry, k, or it's not and, it's or k not equal. So at least the first two indices must be the same, or I mean, so okay, now let me ask you about this. So if I have this is going to become 0. So what it tells me is that the first two indices must be the same and the second two indices. So now I'm putting an and. The first two indices must be the same and the second two indices must be the same. So ij must be equal to, say, or in other words, is so this is fine. So you will get that aij kl equal to 1 if I equal to j and k equal to 0. Okay. So here it is if I not equal to j or, and now it will be that it's equal and k equal to. It doesn't tell you that, so I can get a11, a22 will be 1. It doesn't tell you that the first and the third index must be the same. Okay. So you have got this, fine. So you actually know all the elements. Now the next thing is to show that this is an isotropic tensor. So how does one show it's an isotropic tensor? By definition, what is an isotropic tensor? It's that a prime ij kl must be the same as, so if this is satisfied for any arbitrary rotation transformation, then A is an isotropic tensor. So use this. So now a prime ij kl by definition is going to be delta prime ij delta prime kl. So your by left hand side by definition will be equal to delta prime ij times delta prime kl. But we know that this is isotropic. So this is going to be delta ij delta kl. And this is nothing but aij kl. So therefore you can see that this is really an isotropic tensor. So it is a fourth rank tensor which is isotropic. But this is not the most general fourth rank isotropic tensor. Now convince yourself that the most general fourth rank isotropic tensor can be written in this form. Yeah, write it as C. So this is the most general fourth rank isotropic tensor, where this lambda 1, lambda 2, lambda 3 are some scalars. Or in other words, what we have done is I have constructed an isotropic rank 4 tensor from the second rank isotropic tensors. Okay. And you can see the way we have done. I've taken ijkl, then ikjl, and ilj. So I can only get 3 of them because it's like C2 by 2 factorial. Okay, let me ask you this question. Since I also have an isotropic third rank tensor, so you may imagine that I can contract. So I can combine, for example, this with this. So in principle, what should I get? Epsilon ijk, so delta lm. What will be the form of this object? Suppose I call this as aijklm. How should this transform?
Tensor rank 5.
And tensor rank 5, right? Now this is, again you can show by the same argument which I did, that this is going to be a fifth rank tensor which is isotropic. But now from a fifth rank tensor, I can contract a fifth rank tensor in 2 indices and construct a third rank tensor. Right? So suppose I get, because we can see that Okay, now you people tell me what answer should I get for this? Sorry. What will this give me?
Rank 3 tensor.
Rank 3 tensor, but what will be the form of that? Okay, so I'll write this as some, let's write this as some B, I, K, N, I, J, N. So this is going to be now a rank 3 tensor, right? Now, what will be the components of this object?
Levis-Beta tensor, same as Levis-Beta tensor.
That's right. So you will see that you won't get anything different from your Levis-Beta tensor. Okay, verify that. Okay. So the most general isotropic fourth rank tensor, I said, you can show that I can't get anything else. I can only get this. Okay, now I'm going to do something. Yesterday I showed you an identity. Okay, and now we will use the tensorial arguments to prove that identity. So yesterday I showed you that epsilon ijk, epsilon kn will be equal to, I don't know how did I show it, which way I used. Let me just use the same form I used yesterday. Okay, never mind. Even if I don't know which form I use, but anyway, you can take it from me. This is also correct. So it's delta IN, delta JN minus delta I. Because I don't know whether I use the K here or whether I use the K here. So that's all I'm saying. Delta IN, delta G. Okay, but this is also correct. All right, so I told you that epsilon satisfies this property. Okay, now one way of proving this, as I told you last time, was that you actually explicitly take first of all, the antisymmetry properties are there, and then after that, what you do is construct different elements and show that the right hand side is satisfied. Or you can use the fact that this is a 6th rank tensor and I'm contracting it. So if I contract a 6th rank tensor, I should get a 4th rank tensor. And it has done this. So now I'm going to use the second way of doing it. That this, so take epsilon ijk, epsilon nln. This by definition must be a 6th rank tensor. So let's call this as bijk nln. Because I've combined two 3rd rank tensors. Now I've contracted this. So by definition, this must be then a 4th rank tensor. Because if you contracted a 6th rank tensor in 2 of its indices, then it must be a 4th rank tensor. And further, what you can see is that even before I contract, suppose I just did NLM here. Now this on the right hand side, this is an isotropic tensor because epsilons are isotropic. And you can show now by using the same argument which I just gave initially, you can show that this quantity, this 6th rank tensor is also an isotropic tensor. Because the argument is same, B prime will be equal to epsilon prime times epsilon prime. And since epsilon prime and epsilon prime are the same as epsilons, B prime will be the same as B. Okay. So this is a 6th rank isotropic tensor. And then I contract 2 indices. So whatever object this is now a 4th rank tensor. And because it is isotropic, the 6th rank, the starting 6th rank tensor was isotropic. This corresponding contracted 4th rank tensor is also isotropic. Now this is a 4th rank isotropic tensor. So the most general 4th rank isotropic tensor is this. So I can simply say that whatever this answer is, it should be equal to this. So I can write this as delta, and you can see that now it has to have only these indices ij, lm, because I summed over k's. So I can get ij, delta lm plus delta il, delta jm with some coefficients. lambda, and then I get I in and delta G. Okay, because your right hand side must be a fourth rank isotropic tensor, and since I've already told you that the most general fourth rank isotropic tensor is this, where these lambdas are scalars, I can only get this. Because and the free indices, as you can see here, are just I, J, N. So I simply have to permute those free indices. And now these lambdas, because these are scalars, they can be just numbers, because you know that this is isotropic. I cannot have lambdas depending upon any coordinates. So all I need to do now is to fix the lambdas. Okay. Now what you can see is that from this left hand side, this is going to be antisymmetric under exchange of ing. Correct? Because epsilon is antisymmetric under exchange of ing. So your right hand side must also have the property that it must be antisymmetric under exchange of ing. Now if you want the right hand side quantity to be, because you can see that this is a tensor of fourth rank tensor, this is also a fourth rank tensor, and let's call this now simply as sub C ij lm, okay, by definition. So this is a fourth rank tensor with ij lm. It is antisymmetric under exchange of indices ij. Now this is also a fourth rank tensor. This must have the same property as this, that it must be antisymmetric under exchange of ing. So automatically what this tells me is that your lambda 3 and lambda 2. So antisymmetry in exchange of ing or under the field. What this tells me then is that your lambda 3 must be equal to minus lambda. Firstly, okay. Because you can see that if I exchange ing, then I'm going to get jm here and il here. So I should get this to be minus of this. And further, it will also tell me that your lambda 1 must be equal to 0. Because this is going to be symmetric under exchange. And I can't get some arbitrary lambda 1, lambda 2, lambda 3, because if I get some arbitrary lambda 1, lambda 2, lambda 3, then I will not have this nice antisymmetry property. So again, I want to recap the arguments. So the first thing is this: this fourth rank tensor is a contraction of two sixth rank tensor by contracting in two of the indices. Then using the antisymmetry property, that this is now a fourth rank tensor with this antisymmetry property, which is coming from the fact that it has been constructed from two antisymmetric epsilon tensors, I can simply use that argument and say that whatever these numbers are, lambda 1, lambda 2, lambda 3, it must satisfy this condition. All right. So then immediately it tells me that I just have to have simply this, and I can simply write this as lambda. So I'll write this as now lambda 2 times delta il delta gm minus of delta. Actually, now I've just reduced to finding out one number, lambda 2. Okay. So for finding out lambda 2, what you do is just put put the values for this. So take ij ln. So for example, what you do is take epsilon 1, 2, and then I have k. Then I have k here, and take here you take it as say 1, 2. Okay, I can take 1, 2 here. So fix say. So I put 1, 2 here, and I put 1, 2 here. So once I put 1, 2 here, then the only option I get for this will be that 3. Because I'm summing over k here, but I can't get any other k except 3, which will give me a non-zero answer. So I'll get epsilon 1, 2, 3. So this is going to be epsilon 1, 2, 3 times epsilon 3, 1, 2. You will have other terms, but all these other terms will be 0. Because when k equal to 1, I will get 1, 2, 1 and 1, 1, 2, that will give me 0. And k equal to 2 will give me 1, 2, 2 and 2, 1, 2, that will also give me 0. But epsilon 1, 2, 3 will give me plus 1. Epsilon 3, 1, 2 is also plus 1, so I'll get simply 1. Fine. So when I fix ij, so so I'm fixing the values now. Okay, so let I equal to 1, j equal to 2, and then I have taken L equal to 1 and M equal to, that's what. Okay. Then your right hand side now will be equal to lambda 2 into, since I have taken I equal to 1 and L equal to 1, so I'm going to get delta 1, 1. This is going to give me delta 2, 2 because J is 2 and M equal to 2. And minus I'm going to get delta I is 1, M equal to 2, and then this is going to give me J is 2 and 1. But this is identically equal to 0 because delta 1 to delta 2, 1 is 0. So this is simply going to give me lambda 2. So your right hand side equal to lambda 2, and this should be the same as your left hand side, which is 1, which we found out explicitly. So therefore this tells me that lambda 2. So therefore it tells me that I have nothing but so by simply using tensorial arguments, I can show that this must be satisfied. There's nothing else I can do. And I have gone through this argument, or I've gone through this whole thing because you'll find that this is really going to be a very useful, this is a very useful way of dealing with such objects, especially when you, those of you who are going to do advanced quantum mechanics, quantum field theory, and astrophysics, people who will deal with tensors in considerable detail. So often what happens is in physical quantities, we will be having tensors. And by using tensorial arguments, you can actually fix it just like here. I know that this must be a fourth rank tensor, and I also know this must be isotropic. So by simply using the fact that it must be the most general isotropic tensor is of that form, I fix the general form here. And then I can use symmetry arguments, then after that, to find out or to reduce the coefficients, and then later on we fix values by just using certain particular fixed values. Okay, and you will find, as I said, especially those of you who are going to do quantum mechanics and or quantum field theory and astrophysics will find these kind of arguments very, very useful. And it considerably eases the way you do calculations. And you really need to learn how to use such arguments. That's why I have explicitly shown you how to argue like this and figure out identities. Okay. So this is an example of how one can use tensorial methods to get or to work out certain algebraic identities. Now, before I go further, let me say that. See, so far what we were doing was we were discussing, or I said that I'm going to define a tensor in this form, that a tensor of rank m is something which has 3 to the power of m components, and its transformation properties under a rigid rotation is of this form. This is what we will see. And I've also chosen all of this with determinant r equal to plus. Okay, this, by the way, are known as proper rotations. So rotation transformations which satisfy this condition that the determinant of r is equal to plus 1 are called as proper rotations. See, what we saw was that the R matrix or the R was an orthogonal matrix which satisfied this condition. And this actually told us the determinant of R can be either 1, plus 1 or minus 1. And I have restricted so far to this proper rotations. Okay. What are called as proper rotations. Now the ones which have determinant of R equal to minus 1, they are known as improper rotations. Note that if you think about it from our axis point of view, the rotation transformation is something which is taking you from x, y, z to x prime. So if I think in terms of coordinates, x prime, y prime, z prime equal to r11, r12, r13. This is what it is. Now, can you tell me, I mean, by looking at this, and I want a transformation matrix R such a way that determinant of R equal to -1. It must be orthogonal transformation. It must be an invertible transformation, and obviously because determinant R is not 0, and which has -1 as a determinant. Can you at least give me an example of that? By just looking at it.
Minus cos theta,
Minus cos theta.
minus cos theta, sin theta, sin theta,
One second. Minus cos theta, sin theta. Then
0,
0. Okay.
and then sin theta, cos theta,
Sin theta, cos theta.
0,
Yeah.
0, 0, 1.
Okay. So the determinant of this you can see is minus cos square theta minus sin square theta. So that is going to give me -1, and it's going to be multiplied with 1, so it's -1. Okay. And what I'll do is I'll make it even simpler, perfectly correct. So I'm going to even remove theta. Let's put theta equal to 0. So if I put theta equal to 0, I'm simply going to get this. What you have said is perfectly correct. That's a perfectly correct R, which has determinant R equal to -1, but I'm making it even simpler. Because even if I put theta equal to 0, then I'm going to get minus cos theta will become -1. This will become +1. Sin theta is going to be 0. And you can see that this is an orthogonal transformation, because you can see that if you take any two row and just multiply these elements is 0. Similarly for this, and again the length of, if you take the square of each of these rows, you'll get 1. So it satisfies this property. And further that this satisfies determinant R equal to -1. But now if you think of R being put here, what is it? What is this actually doing? Basically, what is this doing? So I'm going to write x prime, y prime, z prime equal to this times x, y, z. So what really are these transformations?
Reflecting x coordinate.
Pardon? Yeah, can you say it again, please?
Reflecting x coordinate only.
Yes, very good. So it's basically x going to -6, y goes to y, z goes to z. Or in other words, you think about it from your coordinate axis. So I'm reflecting the x-axis about the, and so I put a mirror here and then just taking a reflection of my x-axis. So x is going to -6. Okay. So this is one example of a trans R matrix, which is, or a rotation matrix, which is going to have determinant R equal to -1. I could also put this. Again, in that case, I'm going to get, so in that case, what I'm doing is completely an inversion. This is known as a parity transformation or an inversion transformation. Because now I'm doing x goes to -x, y goes to -y, z goes to -z, or R goes to -r. Or if you like, I put it as x goes to -6. So this is a parity. This is known as an inversion transformation or a parity transformation. But suppose I just did two of them. Only x goes to -x and y goes to -y. Will this satisfy this? I mean, will that satisfy determinant R equal to -1?
No.
So what you can see therefore is that I have to actually reflect odd number of coordinates. Either I have to reflect 1 or 3. You can show that this actually will correspond to a rotation by 5 about the z-axis. Because you see, if I rotate about the z-axis by pi, I'll get a cos theta, which is cos pi. Here also I'll get a cos pi. Sin pi will be 0. Cos pi will give you -1. So therefore, this is not a reflection transformation, but it's a rotation transformation. So if I take, okay, so to come back, what you can see is at least examples of transformations which determine R equal to -1 or improper rotations are those with an odd number of reflections. And in fact, one you can show that the most general is that for determinant of R equal to -1, I can take one of these. I mean, I take this -1, -1, -1 times any rotation matrix. See, the one which you showed me earlier, minus cos theta, sin theta, 0, sin theta, minus cos theta, 0, 0, 1. This is really nothing but -1, 0, -1, 0, 0, 0, 1, 0, 0, 0, 1 times a rotation matrix, a proper rotation. So any arbitrary rotation transformation, now I'm going to give you a statement. We'll again come back to this when we talk of rotation group, but I'll just say this now. So any arbitrary rotation transformation now, irrespective of determinant of R is +1 or -1, can be written either as an identity times a proper rotation, or what I will call as Rp, which is by definition -1, 0, 0, -1, 0, 0, 0, -1 times a proper rotation. Now, can you tell me the identity transformation? Is this a rotation transformation? This identity, if I take this one, is this a rotation transformation? Does it satisfy this property?
Yes.
Yes.
So it is a rotation
Yeah.
transformation. Now, what kind of rotation is it? Is it a proper rotation or an improper rotation?
Proper rotation.
It's a proper rotation because you can see determinant of R. So my statement now is that any arbitrary rotation transformation is either can be written as either a proper rotation itself or a proper rotation times Rp, where Rp is this. So now let's ask, so since I have already dealt with proper rotations, I just have to worry again for improper rotations. I have to just worry about what happens to these quantities under reflections or under Rp, or more correctly under, or more explicitly under parity or inversion. Okay, so we have had objects. See, now what we have discussed is objects like quantities like scalars, which we said do not transform at all under proper. And now I'm going to use the word proper rotation to this type of rotations which have determinant R equal to +1. So under proper rotations, what we have seen is that scalars doesn't change at all, whereas vectors transform in a particular way, second rank tensors transform in a particular way, and so on and so on. Now let us ask what happens to these objects under reflections. Because once I know under reflections or under Rp, then I know for any arbitrary rotation, because yeah, I have to mention this. I don't know whether I mentioned this earlier, but you can see from here. So one more thing I will do before I go to that. So I have this. Let's assume now that suppose I have R is a rotation matrix. Let's R be a rotation transformation. So I've gone from one basis B to another basis B prime by this rotation transformation. And let me call this as R1, or let's put it as R. Now from this basis, I go to another basis B double prime by another rotation transformation. Let me call that as M. Okay. So let R and M both be rotation transformations. So I've gone from basis B to B prime by R, and then from B prime to another basis B double prime by M. So what this means is that R is a rotation transformation. So R transpose R equal to identity equal to RR transpose. And because M is also a rotation transformation, M transpose M equal to identity equal to M transpose. Now, so if you again go back to my way of doing this, it was E1 prime, E2 prime, E3 prime equal to R. Okay, so let's write it like this. EI prime equal to RIG. This is how we right? And similarly, you can write that EI double prime will be equal to MIG EG prime. That's what this means. Because this is taking you from B prime to B double. So EI prime is RIJ EG, EI double prime is MIJ EJ prime. Now what I want to do is relate EJ to EJ double. This basis to B double prime. Okay, that's what I want to do. So I can write from here that Ej double prime, from here you can see that Ei double prime is equal to Mij Ej prime. But this is nothing but Mij times Ej prime I can write as equal to Rjk. So therefore what I find is that this can be written as Mij Rjk. And whatever is this resultant, let's call that as B. So my Bik is nothing but Mij. You can see that's really it's like multiplying two matrices because this is like multiplying. So it's like M times R. Or if I write it in the compact form, B is equal to MR. Now the question I want to ask is, does this also constitute a rotation transformation or not? How will I decide whether that constitutes a rotation transformation or not? So I can write this as Bik, well. So now how will you decide whether Ei double prime equal to now Bik Ek? Now how will you decide whether this transformation is a rotation transformation or not? What will you do to prove that? Or what do you need to do to show that? Or, I mean, if you want to decide.
MB transpose into MB.
Yeah, so what you want to just check is whether this satisfies the properties of a rotation matrix or not. So I want to show whether, or you just want to check whether this B satisfies the definition of being a rotation matrix. So remember this definition. So if it satisfies this definition, then it's a rotation matrix. So all I will check is whether B transpose B equal to identity equal to B transpose or not. Okay. So for that, what I will do is explicitly write what is B transpose B. By definition, B transpose will be this. So from here, again, I'm using here matrix form. So this is going to be R transpose M transpose. So I'm going to write this as R transpose M transpose. And B is nothing but MR from here. But M satisfies the fact that M transpose M is identity. So I'm going to get R transpose identity R. And this you can see is nothing. So therefore you find that your B transpose B satisfies that its identity. And similarly, you can show that B transpose B. Or in other words, what this is telling you is that if I do two successive rotation transformations, that again becomes a rotation transformation. That's what this is doing. Because this is what I've done here. I made first one rotation transformation, then another rotation transformation. And what I find is that the combination of the two is again a rotation transformation. Okay. So I've used this fact now so for example, when I told you that any arbitrary rotation can be written as a product of a reflection times a proper rotation or identity or simply as a proper rotation, I've used this fact that two successive rotations lead to a rotation again. So now, as I said, what I want to do is concentrate now on. So it is enough for me. So now if I want to talk of any arbitrary rotation, irrespective of whether, since I already talked of determinant R equal to +1, and I've told you for determinant R equal to -1, any arbitrary one I can write it in terms of RP times some proper rotation. It's enough for me now to ask what happens to these tensors or what happens to the properties of tensors under determinant R equal to -1. So how do they transform under this reflections? Now let us see our usual objects before we get into tensors in general. Let's just see our usual things which we know in geometry or from our usual physics. So again, we are in three-dimensional space. So this is my x cap, y cap, and z cap axis, and this is my origin. And let's say I have the point here, and this is my position vector. So I put it as R. Now, what happens to R, the position vector in reflections under parity? So the position vector is R, and it's given by x, y, xyz or x1, x2, x3. So under inversions, what happens? So when I tell inversion, it means all the three are being reflected. X going to minus x, y goes to minus y, z goes to minus z, or equivalently, x1 goes to minus x1, x2 goes to minus x2, and x3 goes to minus. So under inversion, what happens? R will go to minus. Agreed? So if this is equal to minus x1, minus x2, minus x3. So inversion means RP, which I've already defined. Okay. Now let's take the momentum vector, for example. Another thing. So momentum vector P is by definition what it is? MV, which is nothing but M times dr by dt. I'm taking for a point particle of mass m. And let us say that its position vector is given by R. So classically, I can simply write its momentum as M V, which is M dr by dt. T is a time. Now, how does this transform under R? Under inversion? How does this transform? Again, P has three components, P1, P2, P3. M is a scalar, V is a vector, time is a scalar, so dr by dt will transform like a vector. So this has three components, it will transform like a vector. So how does this transform under inversion? And maybe I'll also put spatial inversion here, just so that you know that I'm only taking this space coordinates. Anybody wants to say?
In the same way, like the position vector transforms.
So it will simply, all the signs will get changed. So P will go to minus P, which will be equal to minus P1, minus P2, minus P. There's nothing great in that, simply because this is dr by dt. So R has gone to minus R, so this will go to minus M times dr by dt. Because under spatial inversion, neither the mass will change nor will the time change. Okay. Now, before I go further, now let's consider this quantity R cross P. What is this?
Angular momentum.
Angle. Okay, how will this transform under a proper rotation? You have taken two vectors and have taken the cross product of that. What object will I get? Angular momentum is what? How does it transform under a proper rotation? Does it transform like a scalar, like a vector, or a tensor of rank 2, or what?
Like a vector.
That's what. See, we've seen that the cross product of two vectors transforms like. That's what I saw yesterday. Okay, this will transform like. You know it's an angular momentum vector. Why do we call it vector? It will transform like a vector under proper rotations. And yesterday I gave you this compact way of writing this cross product of two vectors. So you can see that I can write this as epsilon ijk rj, or if you want xj pk. So the angular momentum can be written in this compact way like this. Yesterday I told you that if I take the cross product of two vectors u and v, or a and b, then the cross product can be, I can use epsilon ijk tensor to write it. So in particular for the angular momentum, you can write it like this. Okay. So and what we saw yesterday was that under proper rotations, okay, convince yourself again if you're in doubt that this transforms really like a tensor of rank 1. Because again here I combined two tensors of rank 1, so that will become a tensor of rank 2, and then I've taken this third rank tensor, combined it with that, and finally I should get. And you can see I contracted it with two indices. So I should get the first rank tensor. So under proper rotations, it will transform like a vector. But what happens to this object under inversion? How does it transform? Under inversion, what happens to the right side? R goes to? What happened to R under inversion?
Negative R.
It went minus R. P has also gone to minus P. So you will get minus R cross times minus P. And what will that become equal to?
Just L.
Pardon? Just L. So that means your under inversion L simply goes to L. It doesn't change sign. So you can see now I have two kinds of vectors or two kinds of objects, tensors of rank 1. There are these tensors like this position vector, the momentum vector, which change sign completely. All the components change sign under inversion. And then I have another object which also transforms like a vector under proper rotation, but under inversion, it does not change sign. Okay, and you people know the names for this. What kind of vectors are these called usually?
Pseudo vectors.
No, this one, the position vector, momentum vector. Okay, these are called as polar vectors. Okay, so vectors which change sign under inversion, they are called as polar vectors, and this is a vector which does not change sign is called an action vector. This is what you have learned at least, I hope you have learned at least this. So this is an example of a polar vector. So as far as proper rotations are concerned, both your angular momentum vector as well as things like position vector, momentum vector, they behave exactly the same way. Or in other words, that if I take proper rotations, they simply transform like V prime I will be equal to Rij. But under inversion, what you find is that a polar vector or this position vector, there are vectors which change sign completely, and while this doesn't change. So what it means is that it's not that. So what it means is that I have to have an object. I'm having objects now where they are not. I mean, they are both transforming the same way under proper rotations, but under inversions they can behave differently. So I can ask whether the same thing also holds for for other objects, like for scalars or for tensors of rank 2 and higher rank tensors. And what we will find now is that for every tensor, I can have two kinds of tensors. One which we will call as the usual tensor, we don't give any special name for it. It's a tensor. And the other, what we will say, is which doesn't behave in the way we expect it to behave under inversion, or which we expect it to behave. Let me put it like this. I will get this. Now, suppose I have a scalar. Scalar, by definition, what you expect it to do under rotations, under proper rotations. What do you expect? You expect that it should not change sign, right? By definition, scalar doesn't change. Sorry, scalar doesn't change under rotation. Does not change under proper rotation. This is a normal way of thinking about for a scalar. Now you can ask. Now I can have two kinds of scalars. Under inversion, what happens? Okay. Under inversion, I will say a proper or usual scalar is something which does not change under inversion. Because I feel that it should not change. That is my normal behavior. See something like mass wave under inversion. But you will encounter later on, I mean, some places it's possible to find some scalars, which we will call now as a pseudo scalar, which will change sign under inversion. Okay. So for a scalar, I will say that usual scalar is something which does not change sign under inversion, and pseudo scalar now I will say it is like behaving like a scalar under proper rotations. So whether it is scalar or whether it is pseudo scalar, both do not change under proper rotations. But if it is a normal scalar, it will change. It will not change sign under inversion, while a pseudo scalar changes sign under inversion. Now, similarly for a vector, what we found is that normally for a vector, what I would expect is that it is a change sign. So just like the position vector. Under inversion, I expect that it should change sign. So a vector, I will say, or a tensor of rank 1, it will go like this. So I'll have v prime I equal to Rij Bj of proper rotations. Okay, by definition. And then I will now distinguish under inversion two kinds of vectors. The usual vector is something which changes sign under inversion. That means when I say changes sign, means all the components change sign. Okay. And pseudo vector is something which does not change sign under inversion. So what I wanted to emphasize from here is that the pseudo object is actually will depend upon whether it is a scalar or a vector. For a scalar, for a usual scalar, we expect that it should not change sign under inversion. So I will call my pseudo scalar as something which will change sign under inversion. On the other hand, for a vector, I expect that a normal vector should change sign under inversion. So my pseudo vector is something which will not change sign under inversion. All right. So example of this is our position vector. So example is position vector, momentum vector, so on. Whereas for this, the example is the angular momentum vector. Okay. So more generally, then what I can show is the following, that so under proper rotations, it is this, but you want this. So if I can take this and I'll write a more general definition in the following way. So let's first do it for vectors. So vector, we found that Br prime should be equal to Rij Bj for proper rotation, where determinant of R is +1. Now for a inversion transformation, for a normal vector, it should still be the same. Okay. So for this, the transformation properties is still this. But on the other hand, for an inversion, what you will find is that if I take a pseudo vector, then my transformation properties should be equal to minus of Rij. Because you see, why I'm saying, okay, let me put it like this. So if I took Rp, for example, so under Rp, then if I have a normal vector, then I'll have v1 prime, v2 prime, v3 prime should be equal to Rp is minus 1, 0, 0, 0, minus 1, 0, 0, 0, minus 1, v1, v2, v3. Good? This is what I should put. And this will correspond to this particular thing, that it will change sign. On the other hand, for your pseudo vector, I should get, so suppose my pseudo vector is u. Okay, then in that case, my u1 prime, u2 prime, u3 prime should be equal to -1 times this -1, 0, 0, 0, -1, 0, 0. Because I don't want it to change sign under inversion. So this is my RP. This is again my RP. So I have to put this extra -1 sign. Okay. So therefore, what you can see is that for a pseudo vector, and see this -1, therefore I can write it as, so I can write this as determinant of R. So if I write now, therefore, determinant of R times RP, then this is how it will transform under inversion. So this quantity will transform like this under inversion, this quantity position vector will transform like this under position. And under proper rotations, both will transform like this. So now you can see that I can combine the whole thing and write it in the following way, that for vectors, so for a normal vector, I will have vi prime equal to simply ri. Now, irrespective of whether this is a proper rotation or an improper rotation, I will simply get vj. So this is a vector. Okay. And for a pseudo vector, the transformation properties is that vi prime equal to determinant of R times vij. Sorry, rij. So if it's a proper rotation, then in that case, determinant of R is +1. So I will simply get back this answer. And that is what we find. For a proper rotation, whether you have a pseudo vector or whether you have a normal vector, I get the same answer. That vi prime should be equal to rij vj. But if I have an inversion now, you can say that for an inversion, vi prime will be rij vj. So I will get exactly this transformation, for example, for a deflection. While for now a pseudo vector, I have determined R times rij vj. So I will get this extra minus sign now, because determinant R is -1. And then I will get this, and then this will be consistent with the fact that the pseudo vector does not change sign under inversion. So therefore, what we can now we can extend this definition now to pseudo tensors. So most generally, then I will say that tensors are objects which will transform like this. So now, irrespective of whether you have a proper rotation or anything for arbitrary, so for any rotation, so I'm now generalizing my definition. So for any rotation, that means R transpose R equal to identity equal to R transpose R, such that this is there. If I have this object Ti1, I2, In, right? So this is an object with 3 to the power of n components. And if it transforms like this, then this is by definition a tensor of rank n. So this defines a tensor of rank n. And if the object, T prime I1, so the number of components are exactly the same, In equal to determinant of R times T prime I1 Ri1 J1 Ri2 J2. So if I get this extra determinant of R factor here, then I will call this as a pseudo tensor. Okay. So your T is therefore an object which has 3 to the power of n components, and if the T to the power of n components transform like the first line, so I have this object with I1, I2, In, 3 to the power of n components, and if they mix up like this, now this is irrespective of whether it's a proper rotation or an improper rotation. If it transforms like this, then it's a normal tensor of rank n. And if you get this additional determinant of R factor, then you will find that it's called a pseudo tensor. Because you see, this determinant of R will make a difference only when you have an improper rotation. Because for a proper rotation, determinant of R is equal to +1. So you will see for proper rotations, both pseudo tensors and tensors of rank n transform in exactly the same. And you can also see now this is consistent with my definitions which I gave you earlier. For a scalar now, this doesn't change sign at all. So there is no R here. But if you look at this object now, for a scalar, you can see that because you have this additional determinant of R, it will change sign under inversions. Because I have determinant of R equal to -1. For a vector, what will happen is, because if I just did a reflection, I'll just have one R. Now, as we've already seen, under a reflection, all the components change sign. So this part, again, now for a pseudo vector, what will happen? This R, there's one R. So it will change the sign, but because of the determinant of R, which has now -1, finally the sign does not change. Now for a tensor of rank 2, again, what you will find is that there again, you will see that under inversion, for a normal object, it will be like a scalar. It will not change sign. Whereas for the pseudo tensor, it will change sign. Of rank 2. I mean, the components will change sign.
Ma'am?
Yes? Yeah.
This is inversion is an improper rotation, right?
By it's called, that's a term, yes, that's right.
Okay, so this definition of this pseudo tensor, is this restricted only for inversion or in general any improper
This
rotation?
is true for any, this is true now for generally. Because you see, if I have a proper rotation, then your determinant of R will be simply +1. So I will get, so see, what you have is now an object which has 3 to the power of m components. Under proper rotations, whether you have a tensor of rank n or a pseudo tensor of rank n, they transform exactly in the same way. Because you can see that if I have a proper rotation here, if R is a proper rotation, then determinant of R is +1. So putting this extra factor here doesn't make any difference. Do you get it?
Ma'am, but in case of improper rotation, I'm
Yes.
asking improper rotation.
Yes.
This definition of pseudo tensor is true for any general improper rotation, right?
I'm now saying that this definition is true for any arbitrary rotation. It's not just for improper rotations. This is true for whether it's a proper rotation or an improper rotation. What I'm trying to tell you is that if you have a proper rotation, suppose this R was a proper rotation, then these two answers will be the same. For an improper rotation, you will get an additional minus sign here, which you won't get here. Now I'm saying, see, when I gave you this definition, now I'm not restricting myself to either proper rotations or improper rotations. Both are taken into account.
Okay, ma'am. Yes.
You get it? See, because
yes.
if it is a proper rotation, this additional factor will not create any change. Because it's simply like a +1. If it is an improper rotation, then this is going to give an additional -1, and that is going to distinguish between a tensor and a pseudo tensor of the same rank. And again, I will emphasize, to get your physics, to get the ideas in your head, keep in mind the position vector and the angular momentum vector. How they behave. See, both the position vector and angular momentum vector transform like a vector under proper rotations. They both have 3 components. Their properties will change only under reflections. The position vector components change sign under reflection. All the components change sign, while for the angular momentum vector, all the components remain of the same sign. So you keep that example in your head, and then, as I said, it's just generalized. And this definition now is for any rotation. See, I've written here for any rotation. It doesn't matter whether it's a proper rotation or improper rotation. So does that satisfy you?
Yes, ma'am. Yes.
Yeah. Okay. So, so it's now 12:30. Do you people want a break or should I continue? Yeah, somebody should say something.
Ma'am, if you can continue and leave a bit early.
Yeah, okay, I think that is better. Yeah, I think that's good. Yeah, I do that. See, and one more thing I want to say, see, under reflections, what is happening is, I mean, if you, it's also useful to keep some geometrical picture also in mind always, not just mathematical things. So when I'm doing this reflection, x goes to minus x, y goes to minus y, z goes to minus z. See, usually when we have a coordinate system, we have I, j, k. These are unit vectors along x-axis, y-axis, and z-axis. And we have chosen a right-handed coordinate system, by which we mean that, see, the x, I cap cross j cap will give you k cap. Then j cross k will give you, when I say cross, it's a cross product. J cross k will give me I cap, and k cross I will give me j. So it's like 1, 2, 3. So 1 cross 2 gives me 3, 3 cross 1 gives me 2, and so on. So it's a right-handed coordinate system. So that's what we do when we do the cross product, because I cross j will give me k. But if I do this under this reflection, see, I will go to minus I, so it will go like this. J will go to minus j, and k will go to minus k. Okay. And what you can see then is that a right-handed coordinate system will transform into a left-handed coordinate system. Okay. Or in other words, now what you will find is that your I cross j, if you look in the new basis, I prime cross j prime base, I prime cross j prime, you will get not as k prime, but you will get minus k prime. See, whenever we take the cross products, and in school also we've learned that we take this thumb rule, right? Or there's a rule like this. If I take these two vectors, then this is the third vector. So there we are actually taking our handedness into account. If you try to do this with the left hand, you will get a minus sign. So just keep in mind this particular thing, that when I do a reflection or an inversion transformation, then what we are doing is actually we are changing a left-handed coordinate system to right-handed coordinate system. Oh, sorry, a right-handed coordinate system is being changed into a left-handed coordinate system. Okay, now what I want you to prove is in a more general way. So I'm going to give you an exercise. So take this cross product. So again, let's take our angular momentum vector, R cross P, fine. And what we have seen is that I can write this as epsilon ij k xj p. This is a compact. Now use this tensorial way of writing the angular momentum vector components and use the transformation properties. So now use this definition, use this to show that L is a pseudo vector. So in other words, what I want you to do is use this, find out the transformation properties, because Li prime should be equal to determinant of R times Rij. That means show that Li prime equal to determinant of R, Rij, Lj. That is, show this. Okay. And for that, use this tensor identities. That means use this tensorial definition. And use the properties of your epsilons. Remember, I gave you some identities between the epsilons and determinants of R's. So use that. Okay. And finally, I would just would like to remark that if you look at another exercise is this, that you have epsilon IGP. We said it's an isotropic tensor of rank 3. Now show that this is a pseudo tensor of rank. So the Levi-Civita tensor is not just an isotropic tensor, but it's also a pseudo tensor. Let me show this. Okay. So far what we have talked about is, most generally I've just talked of tensors, and we said that a tensor of rank m, whether it is pseudo tensor or whether it's a tensor, ordinary tensor of rank m, it has components 3 to the power of n components. 3 to the power of n components. And it's labeled by this many indices. M indices. Okay. This is a tensor. And its transformation properties have this, the way I've defined. Now, just like what you have seen is in your ordinary, at least earlier, we used to talk of scalars. So, like mass is a scalar, time is a scalar. Then I had vectors, position vector, momentum vectors, and so on. But later on, people studied more interesting objects, like say a scalar potential. This is in electrodynamics. Then you talked of a vector potential. I'm taking examples from electrodynamics. Then you talked of something called an electric field, magnetic field. Now, scalar potential, how do you represent that? In your electrodynamics. Okay, forget about the scalar potential. For the minute, electric field, how will you denote electric field? I just want a simple.
Minus del V.
No, before you had minus del V, we have first a symbol for the electric field, no?
E vector, E bar.
So it is E bar. So it's a vector quantity. And then you also have a dependence on X and possibly also on time. Correct? So most generally you write, and let me forget the time for the minute. So you have this object E of X. Okay, I'll put it as R because we have been using R for the next steps. So what does this E bar tell you? That it is a vector quantity. So which means that I have an X component, I have a Y component, and I have a Z component. And then this part tells me that each of these components can depend upon where I am in my 3-dimensional space. So if you look at my 3-dimensional space, so I have this object now here, which has 3 components, Ex, Ey, Ez, and it will depend upon whether I'm at this position or whether I'm at this position or whether I'm at this position. That is why you call it as a field. And it is an object which is a vector. So this is something, an example of what is known as a vector. Okay, and now of course you people have told me that I can write this. So you have said that E can be written as, so E of R can be written as minus of del V, gradient of V of R. Now what kind of an object is this V of R?
A scalar function.
It's a scalar function, so it's actually what you call as your scalar potential. Because this is what you call as your, I don't know whether you call phi or, so I'll put it as phi, okay? Usually we put it as 5. So this is your scalar potential minus del phi 1. Vector potential is again something which it's a vectorial quantity and it depends upon where I am in my space. Similarly, magnetic field is again a magnetic vector quantity. So now these quantities are examples of something called as fields, which means that they depend upon where you are in your three-dimensional space, because the values of these, for example, if I take the value of the scalar potential, it will depend upon whether I'm at the origin, whether I'm here, whether I'm here or here. So for example, if I have a point charge here, then phi of r is equal to or is proportional to 1 by r. So if I'm here, it's going to be very large. When I'm far away, it's going to be very small. Okay, so it depends on where I am. And when I talk of a scalar potential, it's just one quantity. On the other hand, when I look at my electric field, it's actually a set of three quantities. And those three quantities will depend upon where I am. And of course, you people know that these are called as fields. So you have then now objects which are, so this I will call as a scalar field. This is a vector field. So this is a vector field. So in the same way, I can ask now, can I generalize this concept to tensors? See, just like we generalize the ideas of scalars and vectors to higher rank objects or to objects which transform in some specific way, so I can ask the same thing. Then also before we go that, why am I calling this as a scalar and why I call this as a vector? Field part is because it has a dependence upon the positions where we are. But why do I call this a scalar? Why do I call this as a vector? So again, you can see that by definition now, a scalar field, or if you look at, so keep the scalar potential because it's very useful to keep this two in mind when we understand this. So if you think of your electrostatic potential, phi of r, then a scalar field is by definition something that, so if I'm in one coordinate system, or again, I'll go back to my basis. So if I have V equal to E1, E2, E3. So it is some object which is one object. That means it's only one quantity, but now this is dependent upon where I am. And if I now take this same object and ask what is it with respect to another coordinate system which is rotated with respect to this or another basis, then by definition, you see now what I've done two things here. This phi of r is a function of r. So with respect to the basis B, you have some object phi of r. Now with respect to the basis B prime, where you have changed this say by rotating to something else, my field has, or my scalar field has changed to, the r has gone to r prime because the coordinates have changed, the position coordinates have changed. In addition, the functional form of these phi's can also change. But if it is a scalar, then this whole quantity must be the same. So phi prime of r prime must be the same as phi of r. Okay, if that is true, then I will call this as a scalar potential. Or I will call this, sorry, as a scalar field by definition. Okay. So again, I want to emphasize, so with respect to B, basis B, I have something which a quantity, one single quantity, which is dependent upon the position, and it is some function of R. Now, with respect to the basis B prime, the functional dependence, F can go to F prime, that means phi has gone to phi prime here, which because I'm denoting the functional dependence by phi, and in addition, the position coordinates are changed. And if this is true, that is, if phi prime r prime equal to phi of r, then I will say that phi of r is a scalar. Now, in a similar way, I will say that a vector field is something which will transform just like our vector. So now a vector field is something which will have three components. And let me. So I'm going to denote my vector field by an object which is having three components. And again, we are talking of three-dimensional space. So I have Vi of R, I equal to 1. Or more generally, I can write this as V of R. So just again to keep get some fixed ideas in your head, think of your electric field. You have Ex, Ey, Ez. So it's like E1, E2, E3. And each component itself will depend upon where you are. And the dependence of each component on the position can be different. So you can go back and look at your electrostatics and look at the various examples or various problems you've solved, and you can see what is happening. Okay. So I have now an object where you have three components. Each component depends upon the position. And if now the transformation properties. So again, I've gone from this basis B to basis B prime. And if the transformation properties are like this, then B is called a vector. Okay, for now, again, I've restricted myself to proper rotations, so I'm not taking the determinants for now. So you can see I have V cap, V bar of R bar. So it's something which has three components, and each component again depends upon the position you have. And again, I want you to notice that what I have written here. So we have Vi prime of R prime equal to Rij Vj of R. So in this side, I have R here, I have R prime. Okay, I will mention this a little bit. I'm doing here what is known as, I've taken into account something called as a view which is known as a passive viewpoint. I'll mention this a little bit, as opposed to an active viewpoint. Okay, so now what I can do is I can generalize this again to higher tensors. So now I'm going to say a tensor field. So I'm going to define now tensor fields in the following way. That it's an object which has, so I have I1, I2 up to Im. And each of these components now depends upon your position. So I have 3 to the power of m components. And all components or each component depends upon R. And if T prime, I1, I2, Im. Okay, I'm going to now write it directly. So if it's equal to Ri1, J1, Ri2, J2, Rin, Jn. So it's just that we are generalized the definition, which all that we have put is additionally those functional forms, but that will add some additional Rin, Jn, J1, J2, Jn. Oh. So again here I should put an R prime. Okay. So if this is, so I have an object which has m subscripts, which is each component is a function of R, the position vector. So it's something which has 3 to the power of m components. And if the transformation properties under rotation transformations is like this, then I will say that this is a tensor field of rank m. And if the transformation properties are like this, then P is called a tensor field and pseudo tensor field. Right. So now what we have, therefore, now we've gone from tensors to tensor fields, and just like we also saw tensors and pseudo tensors, I also have tensor fields and pseudo tensor fields. The only change is that you are getting this additional factor of economy R. So again, what we can, so the tensorial I mean, if writing this, and these are things which you have actually studied already. Yes, I mean, already you have said, for example, I mean, again, as I said, keep electrostatics and magnetostatics in mind, or electrodynamics in mind. That will help you to fix ideas. So you've already told me that E of R equal to minus del phi. Now, what is this actually mean? This is a vector equation, so this is really a set of three equations. So it tells me that E1 of R equal to minus of del by del x1 of phi of R. That's what this tells me. Or if I like I'll write it in the following way. See, because this is really a vector equation. You have E here, which is a vector quantity. This is the gradient, which is acting on a scalar. So this is a set of three equations, and the three equations can be written like this. Now look at the right hand side here. What have you done? Now phi of R, you can convince yourself that the electrostatic potential is actually a scalar potential. For the simplest case, it is very obvious, because if you have 1 by R, let's say if I have a point charge, then you know that the potential is simply given by Q by 4 pi epsilon naught 1 by R. And 1 by R, whether if I go to a rotated frame, it will still remain 1 by R. Q doesn't change, electric charge doesn't change under rotations, neither does your 4 pi epsilon change sign. So that definition of phi prime R prime equal to phi of R remains is satisfied. So the electrostatic potential actually is scalar. I mean, you can, I've done it for the most simple case where you have simply a point charge, but you can show this for any arbitrary charge distribution. But look at this now, a little bit from our mathematical view. So I have del by del x I of phi of x. Now this quantity is a scalar. Right? It's a scalar field, or a tensor field of rank C. Then what we have done now is, on this object, I have taken the derivative with respect to I, xi. That means the xith component of your position vector. So by taking the derivative with respect to this xith position and doing it for I equal to 1, 2, 3, or in other words, taking the gradient, what we have done is, you can see that this quantity, del phi of R, now it transforms like, okay, so using the fact that phi of R transforms like a scalar, what you can show now is that this will transform like the three components of a vector field or a tensor field of rank. How to show that? So let me define this. Okay. So before I get into electric field, so let us just say that suppose I have phi as a scalar. So let phi of R be a scalar. Okay. When I say scalar, it means a scalar field. What this implies is that phi prime of R prime equal to phi of R. Right? Construct this object now. Vj by definition is del by del xj. Phi of R. Now my claim is that this object will transform like a tensor of rank or a tensor field of rank. So let's find out the transformation properties. So this again, Vj is a function of R. So this is true for j equal to 1, 2. So I have three components for this object. Now let us try to find out what is Vj prime of R prime. Now by definition, what should this be? By definition, you see Vj is defined like this. So by definition, this should be equal to del by del xj prime phi prime of R prime. This is by definition. Agree? See, once I've defined some object like this in one particular basis, then the same definition should hold in any other basis. So I've just taken the definition. So it's Vj prime of r prime should be del by del xj prime phi prime of r. But now I can say that this should be the same as del xj prime, and because this is a scalar field, this is the same as phi of r. Fine. Then I can write this now by using our chain rule for. I can write this as del x j prime times del by del x k of phi. So when I went from this step to this step, I've used the chain rule for derivatives. Agree? Okay. So now let's look at this object. Now what is this quantity? Del by del x k of phi of r. What is this quantity? By definition, what is this? This is by definition pk of r. So I'm going to get therefore del x k by del xj prime bk of r. And again, I want to tell you that this is a repeated index, so I'm actually having a summation over k. This is k equal to 1, 2, 3. I've summed over all. It's like, suppose this was del by del x. So del by del x prime will be like del x by del x prime into del by del x plus del y by del x prime into del by del y plus del z by del x prime into del by del z. So this is summation. Okay. All right. Now you can see that how are x and x primes related? We know that xj prime equal to rjk x, right? Or x prime equal to rx, if I think about it from the point of view of vectors, right? Okay, I will not put it like this, I just put it like this. Okay. And what is the inverse relation for this? This will tell me that x will be equal to r inverse x prime. So if I use that now, see when I write this, this means this, and here it means then. This implies that your x k, from here you can see that it means x k equal to r inverse of kj xj in component forms. But r inverse is nothing but r transpose of kj xj prime. So we just give you xjk, rjk xj. Fine. So your xk is related to xj prime like this. So therefore this tells me then that del xk by del xj prime will be equal to nothing but rjk. So therefore you can see that I can write this then as equal to rjk dk of r. Or in other words, what we have shown is that, or I've shown that vj prime of r prime equal to rjk dk of. Or if I define therefore, given that phi of r is a scalar field, if I construct the gradient, because this is really saying that I am taking del by del x1 of phi of r, del by del x2 of phi of r, and del by del x3 of phi of r. If I take this set of three objects, then this set of three objects transform like a tensor field of rank. That's what we can show explicitly. And therefore, in your case, and now that if I go back to the example which you given to that particular physics problem or physics example, so that if I have my electrostatic potential, and now if I put this extra minus sign, the minus sign shouldn't change anything. So our electrostatic potential is a scalar. I've taken now the gradient of this, constructed the set of three objects, and then this set of objects, if I call this as P of R, so this transforms like a tensor field of rank. tensor field of rank. Or a tensor field of rank 1 is nothing but a vector. Anyway, you know. Also, you can see now that just like again we saw that from given a vector field or given a vector, I can contract or I can construct from that given two vectors, I can construct two scalars. Now here I can do something more interesting. Suppose my V of R is a vector field of or a tensor field of rank 1. Okay. So you can see I'm taking V, it's a vector and it's a vector field. Then let us take this quantity del. How will this transform? Okay, by definition, what will this be? What is this going to be by definition? Del dot V of R, where this V is a vector field. Or if you like, don't like A, let's see. What is this by definition?
It's a scalar.
No, but I mean, let's expand it first. I mean, write it functionally first, what it means.
Del xi ai.
So this is like del by del x1, a1. See, I'm writing this very elaborately because you will see that it makes sense afterwards. I mean, when you generalize how these things go ahead. Okay. Although you know this, I know that. So del by del x2. And note I'm putting always I'm putting my subscripts. I'm nowhere any kind of superscripts or anything. All right. So which in our repeated vector notation, repeated summation notation, I can simply write as or in other words, what this tells me is that this object is actually just one object because it is simply the sum of these quantities. It's one quantity. And now if you ask that given that your A transforms like a vector field, then how does this transform? You can show, okay, verify that transforms like a scalar. We'll do more with this because now you can see that this particular gradient object, it's like, see this quantity, it's like as if I contracted a vector field with a gradient here, I mean with another vector object and got a scalar. So the gradient is really like again a vector field. But as I said, I'll go back to that later. So given a vector field, now I can construct a scalar by doing this. So here, of course, I've taken what is called as a divergence. And again, this is something which is familiar to you. So for example, if my A was electric field, what is del dot E? What is this? E, I mean, just now we have shown that E transforms like a vector field. The divergence of E, what is it equal to?
Rho by epsilon.
Rho by epsilon. So where rho is your charge density. And this charge density, you know, is a scalar quantity. Okay. So the charge density actually now you can say, in fact, I mean, even if you didn't know, now you can say that this is your Gauss law, nothing but your Gauss law. So it tells me that the charge density must transform like a scalar under rotations. Epsilon naught is a constant, it remains that we are assuming here. Okay. Now, given a vector field, I can do further things. So I have suppose a vector field. Now I can do this. So I can again construct an object which has two labels. Okay, I've taken now the derivative again with respect to, or you can think of it as I've taken the gradient of this vector field now. Where I took the divergence, I constructed from the vector field a scalar quantity, Here now I'm taking the gradient of my vector field, and now you can show that this transforms like so. How should this transform? What do you expect it to transform?
Tensor of rank.
So that it transforms like a tensor or a tensor field of rank. In particular now, if you go back to your electromagnetic theory, electrodynamics. Consider this object. You have the vector potential. This is your usual vector potential. Okay, maybe I'll give this example a little later. We'll construct the object a little later. Okay, so before I go, let me do one more thing before I before I get into physical applications, I just want to know. Now, once we have these fields, vector fields, tensor fields, scalar fields, you people are also familiar with theorems for involving these fields, vector fields and scalar fields. So, for example, you know what is a divergence theorem? This is Green's theorem. This is Green's, I think that's called Green's thing. That if I take, suppose I have a vector field del dot A, and I don't know whether I should, let me call it as B of R, because I don't know use what do I do? So let A be some vector field, okay? Be a vector field, okay? And again, I'm having in mind that I have my three-dimensional space. And let us say I have this volume V, which is enclosed. So there is a surface S. So I'm assuming that I have this volume V, which is enclosed by some surface S. And I construct this object del dot divergence of K D. And you people know what? Okay, this identity. Nothing but Green's theorem, that this should be equal to S A dot N cap. So what is N cap? So if I have this, if my N cap is the unit vector which is normal to your surface. All of you are familiar with this, right? This is Green's theorem, I think. That's what it's called. So if I have the del dot A R dV, so if I'm taking this is a three-dimensional integral that reduces to a two-dimensional integral over the surface which is enclosing that volume, and with the dot product taken between the vector. So let me also put AR here so that R N cap into these, where N cap is the unit vector which is pointing outwardly normal to S. Again, I am sure you have used this in your electrostatics. So if this was, for example, the electric field, so if I have del dot E dV, then this is going to become E dot N cap ES. And when you people solved electrostatic problems, you must have used this, I'm sure. So find out the electric field, for example, at suppose I take some charge enclosed inside a box or inside a sphere. And if I want to find out the electric field on the surface of that sphere, then if I use this particular theorem, it becomes particularly easy to calculate what is the electric field on the surface of the sphere. So if I replace this actually with E here, then you really would get the integral equivalent of Gauss's law. All right. So this is something which you people are familiar with. Now, if I let me use tensorial ways of writing this, okay? So if I use this now as a tensorial way, so I can write this as del. If there's any problem, I mean, if you're not familiar or something, please tell me. So this del dot A, I can simply write it as del by del xj aj, just like surveying. And this now is going to be a surface integral over aj. So here I have A dot n cap. So I can write it as aj of r nj cap of nj cap. So basically, I again use the summation convention here. Now what I can do is I can extend this now, this Green's theorem to tensor fields, higher order tensor fields. So you can generalize this to, again, as I said, all this will become very useful, especially as in context of astrophysics and quantum field theory. So if I have now a generalized, so let me write this as Ij here, or Ik, let me write. So if I now have a tensor field which is of rank n, of R, so then the integral of this tensor field over dV, so it's integral of the Ti1, so I've taken the divergence of this over the ikth index, so it's like x del by del x ik, so I've sort of contracted these two here, and then taken the integral of this. This will be equal to the surface integral on x. Then you have Ti1, I2, Ik, In of R dot Nik. So I can generalize my Green's theorem, and in fact I'm also going to do Stokes theorem. So this converted the divergence, the integral of a divergence to a surface integral. That's what the Green's theorem did for a vector field. Now what we are doing is generalizing that to the divergence of, or I mean divergence in the codes to, you can think of it as a contraction with this del by del xi operator of a tensor field of rank m to a surface integral. Okay. And similarly, I can also do this for Stokes theorem. And you will have very interesting applications of this. I will discuss the applications of such identities or such generalizations a little later. So, what does Stokes theorem do? Stokes theorem relates a surface integral to a line integral. Right? It relates an open surface integral to a, so you have del cross A of R integral. So this is not a, so if I have this over surface and this is dot ds. See, note that this is a cross product. So it's del cross A dot ds. So this is a surface integral. And this should be equal to a closed line integral over C A of R. Right? So the picture is that you have like this, and then I have some surface, and I have this as my C. So this is my surface, and this is my C, which is enclosing that surface. And again, you must have used Stokes theorem very extensively when you did magnetic field calculations. So if you had given different kinds of magnetic fields, if you want to find out the magnetic moments of magnetic fields are different, sorry, not magnetic. You have different kinds of current distributions, and if you wish to find out what is the magnetic field of those current distributions, you must have Stokes. So again, I can generalize this particular relation to higher order of tensors in the following way. That, so I have now a cross product here. So again, using our cross product thing, so I write this. So this particular thing can be written in the following way as epsilon ijk. Okay, so let me write it first. So this particular thing can be written as epsilon ijk del by del xk ak of r times ds. And the fact that I had this dot product here, see, because this is a vector which I have to dot with this ds. When I'm saying I'm dotting with ds, it's a normal which is pointing normal. So this part is this, the ith component of this, then I'm dotting with this. So I dot it with the ni cap. Okay. And then I simply have a ds, which is a scalar. Okay. So this in the tensorial language can be written in this form. So this is over S. And if you look at the right hand side, I can simply write it as AI of R. So when I wrote here DL, so this DL is along this contour C, which is enclosing that surface. Oh, sorry, it is, yeah, eventually it is sort of bounding that surface. Let me put it like that, bounding the surface. So DL is along that. So this, when I write like this, so DXI is this DXI, which is along the contours. So then I can generalize this now to a higher order tensor in this way. So we can write it as epsilon ijk del by del xj of ti1, or let me put it as xik, or let me put it as I1, I2 like this, and then I'm putting a j here. Im of r. Then I have n I cap ds. So if I take this over the surface integral, what will I get? So you can see that what I've done is I've contracted with this j here, all right? Xj is here. I'm missing something. So one second, let me just, yeah, so there should be k here. So okay, look at this object. So this object I've taken del xj of ti1, I2, so k and the jth of this object. Okay, let me use it. Let me use the because you will find it more easy by like this. Don't get confused by this ij, ik I'm using here, and let me use here an l. So I'm using l. Maybe this is better. So I'm using epsilon l, ij, ik. So this ij is contracted with this ij, then the ik here is contracted with this ik. So it's exactly like this. J is contracted here, k is contracted here. So it's exactly like that. The ith index is contracted here, the ijth index is contracted here. I have then an epsilon l. So this object is going to have, this was an mth rank tensor. I've contracted with two indices. So it will become m minus 2, but I've combined it with this one. So it's m plus 1. And then again I've contracted with l. So finally I will remain with the and this is equal to C IM of R not M. So this is what I did. So basically you can look at this. I have taken the derivative with respect to the ijth index. So that's what I want to point out. Ijth index here. So finally this ijth index thing is being contracted with the dxij, which is lying along this contour which is bounding the surface. So this is a generalization of Stokes theorem to tensor fields of higher rank. And this is a generalization of Green's theorem to tensor fields of higher rank. So basically the first one converts the volume integral to a surface integral, and the second one converts the surface integral into a line integral. And again, I would like to say there are really huge applications of such these theorems, and we'll discuss this a little later when we come to applications. Now, let me just take a little bit more. I'm going to now, this sort of, at least for Cartesian tensors, it's sort of, I said as much as I could perhaps in this time. But now what I will do is I'll discuss a little bit of applications of this, because that's something which I'm sure some of you have already asked me that why are we doing all this. So I will at least try to discuss applications. As I said, the most extensive applications of this, or the most extensive use of this, comes in, especially in quantum field theory and in astrophysics, when you do study things like general relativity and so on. But it's also useful, in fact, it turns out to be very, very useful even in many other places. And I'm going to take two specific examples. One is in classical mechanics. And the other I'm going to talk about when we talk of, for example, the electrical conductivity of a tensor, or electrical conductivity of a material. So let me first, maybe I'll start with the other example first, and then I'll come back to the classical mechanics. So in classical mechanics, one of the most, I would say, the paradigmatic example of using tensors is what is known as the moment of inertia tensor. How many of you are familiar with this tensor? The moment of inertia tensor? Have you studied this in classical mechanics already?
Yes, ma'am.
Okay, so you people are familiar with it, the definition of this tensor? I mean, are you familiar with the concepts like principal axis, moments of inertia, products of inertia, and so on?
Yes, ma'am.
All right. So did you use the tensor language there, or did you use some other way to do it?
No, ma'am. We didn't use tensor language.
All right. Okay. So what I will do is I will recast. So these are things which are already familiar to you. But what we will do is we will just recast this in a language which is going to be, which will find that it will become actually very easy to use. Okay. Now, so that is something which I do. So this is a, as I said, this is a very, very standard, example for tensors. In fact, that's how at least most of us get introduced to tensors. So that. And the other example which I'm going to give you is this. Consider some material, okay? So let's say that I have some material, like say copper or some mixture of copper with some things. Now, typically you can see that, and I apply an electric field to that material. Then there is a relation between the electric field and the current flowing through that material, because you have applied an electric field to this conductor. So I'm assuming that you have a conductor. So I'm applying an electric field to the conductor. Then there's a current flow across the conductor. So there's a relation between this, and what is that relation given us? Typically, if you have a linear relation between them, I think you people must have usually written it like this. This is your Ohm's law, right? Or a version of the Ohm's law, because it's simply telling you that the current flow across the current. The left-hand side, this is the current density. This is the electric field, and this coefficient here is called the conductivity coefficient. So it depending upon that, it will tell you that even suppose I have copper, then it will tell me that how much current can flow. If I have some other material, say aluminum, then the sigma will change, because it will tell you that if I apply an electric field, what is the resistance? 1 by sigma will give me the resistance. I'm calling it Ohm's law because this is in fact the way we will define resistance. R will be like 1 by sigma. So typically you write it like this. Okay? But really speaking, if you look at the right hand side and the left hand side, so this is an electric field. So these are, that means I can apply the field along x direction, y direction, z direction. And how I choose x, y, z, again, that depends upon me. And here the current flow is also along the different directions. Now, typically you will have that, or more generally, my current density can be written like this. I forget for the minute the R dependence, so let me just take it as sigma actually. And where the sigma ij now is an object which has 9 elements, because it is sigma 1, 1, sigma 1, 2, sigma 1, 3. Okay. And what this tells us, for example, it tells me that J1 is equal to sigma 1, 1, E1 plus sigma 1, 2, E2 plus sigma 1, 3, E2. And depending upon what these values are, there sigma 1, 1, 1, sigma 1, 2, sigma 1, 3, then I will find out what is the current flow across the one direction. Or say, suppose I call the one direction as my x direction. So the current flow across the x direction will depend upon the values of this. And of course, the electric fields you put along the XYZ directions. Okay. So often what you will find is that in materials, that you will not get simply a sigma here. You will get this. Or in other words, what it will tell me is that the values of this will be different. Or in other words, what it tells me is that the current flow, so suppose I put the electric field, let's say that I assume that I put the current electric field only around the x direction. Then J1 will be sigma 1, 1, E1, this part will become 0. Okay, suppose I do this. Now J2 will be according to this definition, E2, 1, E1. Because I put E2 is 0. Okay, so let E2 and E3 be 0. So I have put my electric field only along the x direction. And J3 will be equal to sigma 3, 1. Now, if your sigma 1, 1, 2, 1, so if this are different, then what it tells me is that the current flow along the x direction, y direction, and z direction are different. Or in other words, you need not have an isotropic current flow across all the three directions. I could get different current flows. And sometimes it can turn out that these values are actually identically 0. So it can happen that sigma 3, 1 is identically 0, in which case it will mean that I may not even have a current flow at all along the x direction or a particular direction, say in this case, the z direction. So often you will find that the conductors are really not isotropic conductors, or in other words, that the current flow is not the same in all directions. And this is of course dictated by the electronic configuration of those objects, because it may happen that the current will flow easily across in a particular direction as opposed to some other direction. Okay. So most generally for Ohm's law, you have this, and this particular thing is called the conductivity tensor. Okay. And this, I'm going to show you some examples of this, because in real life you will see that we really need to take an anisotropic. Usually one needs to take anisotropic conductivity tensors into account, and it leads to some very interesting consequences. I'll show you some specific examples here. And similarly, again, we'll do more examples. Similarly, again, if you look at magnetic material. Now, if I take a magnetic material, it means that it has, say, let us say it has some magnetization, so for example, and then I put it in a magnetic field. So if it has a magnetization, it means that it has some kind of a magnetic moment. Now, what can happen to this magnetic moment once I put it in a magnetic field? That it will try to align or it will try to rotate in that field. So that will depend on how much it rotates and whether it will rotate or not. That will depend upon the susceptibility of that magnetic material to your magnetic field. And again, from your electromagnetics, you can see that I'll write it in this form, that you can write this as chi Ig. So the magnetization, so again here we are doing what is known as linear ethics. So I put an external magnetic field and I try to ask how my magnetization changes or a magnetic moment changes. So I find that my Mi can be related to Bj in this. And this particular coefficient, again, this is an object which has 9 elements. This is called the susceptibility tensor. Or in this case, it's a magnetic susceptibility tensor. So again, it's a second rank tensor. And again, as I said, depending upon what kind of material you have, it may happen that a particular magnetic moment will not rotate at all. On the other hand, if I put a magnetic field in a particular direction, it may not even respond to that. On the other hand, it may respond to a magnetic field put in, say, a perpendicular direction, and that will depend upon this chi. And chi will depend, of course, upon the material properties, which again will depend upon, in this case, upon the electronic properties as well as the spin properties of that system, the electronic spins properties of the system. So these physical properties, therefore, like things like electrical conductivity, magnetic susceptibility, and so on, often you need to take tensors, and they are not really isotropic. You need to take them as tensorial objects. So even in our usual, as I said, solid state physics, we need to take these things into account. And we will see that using tensorial language simplifies our analysis considerably. And not just that it simplifies our analysis considerably, it will actually, you will see that this tensorial way of doing things will also help us to understand the symmetry properties of your material. So, see, just like your moment of inertia, since some of you have already said that you're familiar with it. So if you have this principal axis, it could happen that suppose I rotate along a direction which is parallel to the principal axis, then that will become like a symmetry axis. So I'll show you that this particular way of dealing or this particular way of analyzing will help us to understand the physical properties in a much nicer way and give us a deeper insight into what is really happening. So I think I will stop here now because it's already it's 1:30 now. So I'll stop here. And tomorrow I'm going to again take class at the same time. I'll start at 11:15 and we'll again take 2 hours. So at that time I'll deal with these examples, in particular the moment of inertia and this. And we will see how naturally the tensor language adapts to discussing symmetries and symmetry considerations. Okay. So thank you then. I'm going to stop here now.